Hi, in this video we are going to do some pre-processing on top of our Amazon dataset and then store the data that we want and need into a quadrant vector database. And in the next video we are gonna then use this quadrant database and perform some retrieval operations and implement a RAG pipeline. Okay, so now we are pre-processing and implementing quadrant. So for that, I will be creating a new notebook and I will call it 02 RAG pre-processing. And I will also add Amazon because we might have other data sets. I want to distinguish in the name what we are actually pre-processing. Okay, so we'll need few imports. So I'm gonna just go ahead and import everything that we need for this specific notebook. And that will be OpenAI, Pandas, and Quadrant Client. Now, we don't have Quadrant Client installed yet. And that's what I'm gonna do right now. So UV add dev Quadrant Client. So it worked out. Let's see if we have the required dependency. Yes, so we have Quadrant Client installed. It should not complain anymore. So let's import this and let's do some pre-processing before we write into Quadrant. And of course, we'll need Quadrant deployed itself. But before we do that, let's do some pre-processing. So this is a markdown cell. Let's run it and let's read in the items dataset. PD read JSON, and I'm pointing to the dataset where we have items with category, more than 100 ratings, and even that downsampled to 1000 items. Let's just inspect. So I forgot to select a kernel. Now let's do that again. .head. So as expected, we already saw this data frame. We have main category, title, average rating, rating number, features, description, price. So it's not very convenient to actually see what's inside of these columns. So we are gonna look a little bit deeper into that before we decide what kind of pre-processing we are planning to do here. Okay, so let's look first of all into the features column. So features is this. And what I'm doing here is I'm simply taking in the entire column, I'm transforming it into the list, and I'm taking the first element. So basically I will be able to print this specific value right here. And this is how it looks like. So it is actually a list of strings. So that's important because we want to properly pre-process this. So features kind of describes the item. So description, as you can see, is an empty list, and the features are the actual description of this item. And I would go as far as to say that it is title plus features, and that is the actual description of the item. Now, what do we have in images column? Because that is also potentially important to us. We have a list of different images. So each of the list item is a dictionary, and it has different formats of the same image. So if I would click on one of them, I will see that, okay, so this is too small. Let's pick something bigger, large. Okay, so this is just some cords, charging cords, but a very useful, nice addition to the metadata that we have. Just wanted to show you that we have a list of images. Which we will be using in the future. Okay, so what do we want to do first of all? So we want to have this description for the item, and we will be using this description, specifically this description, for retrieval purposes in the future. So I will create a new title, preprocessed title and features, and I'm gonna do a very simple thing here. So not a lot of preprocessing. I want to keep this simple. I'm gonna go ahead and loop through all of the rows in the dataset. And for each of the row, I'm gonna concatenate title with the features. So I'm gonna create a single string out of these two columns. And remember that these features values are actually a list of strings. So we need to concatenate this string, and then this concatenated string, we are gonna concatenate with this string, which is the title. And this is what we are doing here. You're simply taking in the title, and we are combining it with the joint list right here. Then we are extracting the first large image from this one. The list can have multiple images, but we, in this case, in this specific scenario, in this specific application, I will only use a single image. So the first large image from a list of images. And this is what I'm extracting right here. So for the first element in the list, I'm getting the large image URL or an empty string. Okay, and then I'm simply running, we'll be running this pre-processing on our dataset on each of the row. And I can do that by creating a new column and running the df items. I will call this column description. And it will be calculated by applying preprocessed description function on axis 1. So what it will do, it will apply this function on each of the row in the dataset. As a parameter for this function, we are providing the row, and then we can extract any value from the row that we might find interesting. So for us, it is title and features. And the same we are going to do for extracting the first image. And I will just call this new column image, and I will be applying extract first large image function. First large image, run this, and let's inspect the data set. So now we have a description, which is concatenated fields. Actually, we can inspect that. Let's see what we have here. So yeah, one long string properly concatenated. And for image, I think it will be the last column. We have an actual URL to the image of interest. What else? So description, image. Now I will still not work, not yet. I will not work with 1000 items. I want to downsample this dataset yet again, just for quick development purposes. I just want 50 items. So I'm gonna do exactly that. I will take this df items dataset, and I will sample it for 50 items with some random seed. And just to make sure that we have properly downsampled. Let's check the length, and it's 50, so exactly what we needed. Now I will already start embedding the data. We'll get to that. For that, we will need an embedding model and a vector database. But let's just prepare the data to be embedded before that. So data to embed. So for this, I'm just gonna not downsample, but select only relevant columns, which are interesting for me out of this data set. And that will be description, image, rating number, price, average rating, and the parent as SIN, which is the product ID. So of course, I'm not embedding everything, but I will be storing some of the data as metadata in the vector database. So we will be embedding the description, but all of this extra metadata we will be storing as payload next to each of the vector that we will be storing in the database. Now I want to make a dictionary out of this so that it is easier to process. So I'm gonna go ahead and do toDict and orient records. So now instead of a data frame, I have data to embed. I have a list of dictionaries, and each of a dictionary can now be easily processed because I can call items by keys. So I will be looping through 50 of these and performing transformations, embedding, and inserting to the vector database when I need to do that. So the first thing that I'm going to do is actually embed the data of interest. And for that, I will need to define an embedding function. And for embedding model, I will be using a text embedding free small from OpenAI, and creating an embedding for a piece of text with this is very simple. We can use OpenAI's library right here and just call embeddings create API, and this input is the text that you want to embed, and the provided model is the model we will be using to embed it. So let's just, as a test, run this. This is random text, so we are embedding a piece of random text, but the response is basically a vector. So it is a embedding of length 1539, I believe. Actually, we can just check. So if I would go response data dot embedding. Oh, sorry. Dot embedding. Data. Yes. So I take the 0th item and embedding. So now this is a list, and if I would check the length of this list, I will see that it is 1536. So this is the length of the output vector produced by text embedding free small embedding model. So we will need to create a quadrant collection which corresponds to this length, but we'll get to that soon. So this is how we perform the embedding. Now we'll just very quickly create a function, helper function, which will actually help us create those embeddings. So this is it, and we will be accepting with this function, get embedding function, we will be accepting a parameter called text, which is a text that we want to embed. And by default, we'll be using model, which is text embedding free small. We are reusing the same method right here and returning the actual vector now instead of just a response. Okay, so we can actually test it out again. Let's test it out. Get embedding and provide some random text. hi. And we get back already a vector, which is an embedding for this piece of text. Now, the next part of this video involves running a Quadrant database and actually storing this data in Quadrant database. So we will be developing locally and for now, and we will be deploying a Quadrant database locally as well, Quadrant server locally as well. You can learn more about Quadrant by going to their webpage, so Quadrant. Right here, so there's a very nice documentation that you can tap into. It would also have deployment steps, but I will run through the steps you need to deploy Quadrant locally simply. And we are actually gonna go ahead and deploy it via Docker Compose. So we already have an application running, but this is our old application from the prerequisites repository. So what I'm gonna do right now is actually comment this out, because we are going, or actually not, I'll keep it running. But I will introduce a new service right here. And again, if you want to learn about the Docker Compose and Docker and what all of this means, refer to the prerequisites video that I've introduced in the previous video of this week. Okay, so Quadrant. It is a very simple service. We will be using their official Docker image, which is Quadrant, and Quadrant exposes 2 ports. 333 is for HTTP, and 334 is for gRPC. We are only interested about 333 right now, but it is a common practice to expose both. Now, once we launch this database, this server, a folder will be created inside of the container, which will hold all of the data relevant to Quadrant. And now we are mounting this local folder, which we call Quadrant storage, to that folder inside of the Quadrant container, so that all of the data that we do write into our Quadrant server is also persisted locally. And once we restart our Quadrant server, the data is retained, so that we can very efficiently develop locally. So let's save this file and just try and launch the Docker Compose application. And remember, we have this makefile where we have run Docker Compose command, and it should be able to bring up all 3 applications that we have defined in our Docker Compose file right here. It will most likely take a little bit of time, around 20 seconds, I think, usually. But let's see. And of course, my internet can also be a problem sometimes. So it could be connection issues as well. Okay, see, so it's up and running. Everything is up and running. Quadrant, our Streamlit application, demo application, and our Fast API server. Now, we can access Quadrant dashboard via this link, and that's what I'm going to do right now. And let's explore what we have here. So the main thing that you will be looking at initially is the Collections tab. And a collection is how Quadrant organizes its vectors that you store and all of the metadata around it. So you could think of a collection as a table in a regular transactional database. If you have information that relates to each other, you would be storing that in a single collection. So in our case, we'll be storing items in one collection, and we'll be storing user reviews in a different collection. So now we have this up and running, and we can actually go ahead and create a collection where we are going to store our vectors. And this is what we are going to do right now. So first thing, let's create quadrant collection. What's this? Markdown. Let's do Python. Let's add a few more code blocks. And you can create, first of all, in order to create a quadrant collection via a quadrant client, you need to initiate that quadrant client. Remember, we imported it right here. And what we need to do is point to the endpoint where this quadrant HTTP server is exposed. So this is what we do here. And quadrant client has a method called create collection, quite an obvious naming, which allows us to actually create a collection of interest. First of all, we are giving this collection a name. So Amazon items collection 00. That's how I'm calling it, because I sometimes want to version these collections. And if I want to create another collection holding the same data, I would be bumping the version up and would be calling it 01. And each of the collection has its own configuration, vector configuration. So there are a few things that you need to know. You set the size, which is the length of the vectors that you will be storing in this collection beforehand when creating the collection. So since our embedding model, right here, this one, is creating vectors of length 1536, this is also where we need to set the size accordingly, because if we do not, it will not work. We will not be able to write to the database. Now we also need to define the distance similarity metric, which we'll be using to calculate the distance between the vectors beforehand as well. And a industry practice is to use cosine similarity almost always for comparing two pieces of text if you want to search according to contextual similarity. So that's why we are defining this size and distance as a cosine similarity measure. Okay, so it says true, which should mean that we have successfully created a collection. We can check. Yes, so we have a collection, a new collection created. The status is green, which means that we are ready to operate it. And these are the settings that we talked about: the size, the distance metric. You can also name the vector, but for now we do not need that. We'll learn about it a little bit later. So we have created the collection. Now we need to run some embeddings and create a specific structure, which is required for us to actually load the data to Quadrant. So first of all, let's call this section embed data. Let's run some tests beforehand. So test. What do we need to know about writing data to Quadrant? Well, first thing is that Quadrant takes in what we call point struct. So point struct we have imported at the very top right here. And it is just a data structure which is required by Quadrant to be ingested. So there are a few parameters that need to be set for a specific point struct. ID, and this has to be unique per collection, meaning that if you're trying to write something to the ID that already exists, you would be overwriting that specific vector. Now the vector, we are just testing it out. So we are just using some test text, which is passed through our get embedding function. And we can also provide additional data as a payload to this point struct. And this payload can later on be used to either retrieve additional information when running a similarity search, or you can also run pre or post filtering using this data. So for example, if I would have a number here, I would be able to pre-filter on this number. So let's say the number is less than something, and then the cosine similarity would only be performed against the vectors that have this specific condition met inside of the payload data. Of course, there's a little bit more to it, like the fact that you do need to index those payload elements then for efficiency, but you can do that. So point struct. Point struct. Point struct is just a data container which holds ID, it holds the vector, and it holds the payload at the very end. Nothing really confusing, just a properly defined data container. Now, the next thing that we can do is actually go ahead and embed all of the data from our Amazon dataset. What I'm going to do here, mark down a new section, call it Amazon data. And this is what I'm going to do. So I will initiate a empty list of point structs, and then for each item in the data to embed, and data to embed, remember, it is a list of these items. Each of the item is a dictionary. And for the embedding itself, I will be embedding the description. So I'm gonna extract this specific text from the description field and only embed it and nothing else. Now I'm enumerating this list. So this Y will be auto incrementing each time I perform one single point struct creation. And the point struct list will be appended with the point struct with this auto incremented ID, the vector embedding itself, which is calculated here, and the entire payload. So we are storing all of this for each of the vector that we are writing to Quadrant. Why? It holds, first of all, it holds quite a lot of useful metadata that we'll be later on using in our application. But also we want to actually have the text itself, which is not embedded, because we are performing cosine similarity on top of the vectors. But once we retrieve, let's say, top 5 of the vectors we are interested in, we still need to figure out what kind of text was embedded there, because our LLMs, when we are putting the data, retrieved data into their context, they care about this text and not the vectors that were used to perform the cosine similarity search. Okay, so let's run this. And I think it will take around 20 seconds to create. We could make it faster because this get embedding function for now is not efficient because it embeds each of the item one by one. Later on, we are gonna introduce some batching into this, but for now, let's just go ahead and run this like we have here. Okay, 18 seconds. Point structs is now a list of length 50, and we have all of these guys right here embedded, and all of the payload also stored for each of the point struct. Just to make sure that we have 50. Let's run this, and yes, we have 50. Now we can actually write this data to a Quadrant, and it is very easy to do. So write embedded data to Quadrant, and the only thing that you really need to do here is run Quadrant client upsert, point to the collection of interest, and provide a list of point structs, which we already have here. And all of those 50 point structs will be then inserted into our Quadrant database. Okay, let's try it out. It's very fast, 2 seconds for 50 items. Now we can go ahead and look into our collection and see if it succeeded. yes, we have approximately 50 items, and actually we do have actually 50 items and not approximately. And we can see all of them right here. So this is a very nice browser, which we can use to just look from a high level into the items that we have written to our database. So we have the payload and we have the images. It's very nice, but those images are also rendered for us automatically just because we have this link right here. And we also can expand each of the descriptions if we want to look closer into what kind of text we have there. Okay, so we have 50 electronics items here. So everything worked. The upsert worked. Now we can try and retrieve some data from Quadrant. And I will define a very simple retrieval function right here. The function itself is taking in a query, and the query is just a piece of text. And the first thing that we need to do is actually calculate an embedding for that query. And it is very important that we use the same embedding function that we used to embed the actual data, which we will be querying against. We need to use the same embedding model and embedding function to embed our query, for which we will be looking similar items inside of the database. Now for the results, we are going to use Quadrant Client's Query Points API. And for that specifically, we need to point to the collection of interest against which we are performing a query. And then the query itself is the actual embedding, which is a vector. And limit k just means how many items, top items we are retrieving. So anything with the top scores. So we take the scores, the actual cosine similarity, we order cosine similarity from the highest to the lowest, and we're cutting off the top k, basically. So nothing complicated. This function, now we can actually test. So let's mark down a new section, test retrieval, and let's just write something, retrieve data. Again, it first takes in the query itself. So I'll ask, what kind of charging cords do you offer? And I will take 10 items. And I'm interested in points. Let's see. Interestingly, it took quite a lot of time. It shouldn't have. But okay, so we got 10 items returned, and let's see. So the first one is properly labeled, iPhone charger cord, charging cable, lightning cable, which is a charging cable, charger, cable replacement. This is, I think, not a cable anymore. Yeah, so these are not cables anymore, and we actually do see the cosine similarity drop at some point in time, and it seems like it kind of properly drops when we are not talking about charging cords anymore. Okay, cool. So we just showcased that the retrieval works. And this is all that I wanted to show for this video. And just to very quickly recap, we have done some pre-processing on top of our Amazon dataset. We have deployed Quadrant database locally with persistence. And we have embedded a subset of our data using text embedding free small model of OpenAI. Then we have created a new collection in quadrant, which matches the vector size which is being returned by the OpenAI model, embedding model. And then we have written this data to quadrant, and we tested the retrieval capabilities. So that just to make sure that it works. Again, this is what I wanted to show in this video. In the next video, we are going to stitch up a very simple retrieval augmented generation pipeline using the functionality that we have implemented here, part of this functionality. Cool. Thank you for being with me in this video, and hope to see you in